So the main parts of this work I actually did while I was doing a postdoc at KU Leuven University in Belgium. But as mentioned just now, I started at NYU Abu Dhabi as well. So in my talk, I will be discussing how we used symbolic execution to find vulnerabilities in implementations of Wi-Fi, and specifically in the four-way handshake of Wi-Fi. So in the beginning of this talk, I'm going to introduce what symbolic execution is, and I'm going to keep it at a very high level. So if you know some programming, you will understand how this technique works. Then we will discuss a small extension of symbolic execution. So we can apply symbolic execution to implementations that use cryptographic primitives, such as decryption primitives or hash functions. And we do that because we want to apply symbolic execution to the four-way handshake of Wi-Fi. And if you don't know what the four-way handshake is, the four-way handshake is executed whenever you connect to a protected Wi-Fi network. And we found quite some vulnerabilities using this, so we're going to discuss those. And as the talk implies, one of these vulnerabilities allows us to remotely compromise a device. And in our specific case, that's a router. So let's get started with explaining what symbolic execution is. And I will do this with the help of the following example here. This represents a very simple function that receives a network packet, for example, a Wi-Fi packet, and then it will process this incoming packet. And you can see here the first two conditions, the header of this packet is being verified. We can see in the very first if condition, the first byte of the header has to be equal to 1. This can, for example, be the version of the protocol, and if it's not equal to 1, the packet is simply dropped, the function returns. And the second byte must be equal to the length of the packet, and if that's not the case, again, the packet is immediately discarded. And only after the header is validated like that will the actual packet be processed, and here we see in the last line that some division is happening. Now, if we were to test this protocol using very traditional fuzzing, where we simply generate random inputs, then it's actually really unlikely that we will pass these two initial first validation checks. In other words, a lot of our random input will be invalid, and we don't really reach the interesting parts of our program that we want to test. And that means we would waste a lot of CPU cycles, and that's not something we want. But that's where symbolic execution comes in. Symbolic execution is a technique that allows you to systematically explore all code paths of a program. So how does that work? Well, what we do is we mark this data, this input, as being symbolic instead of having a concrete value. That means that at the beginning of this function, this data can represent any possible packet that is valid. And we then execute the program on this symbolic input. Now, how does that work? Well, let's say that we encounter a branch, an if condition that uses this symbolic variable. Well, right now, this symbolic variable doesn't have any concrete value, so both branches of this if condition can be taken. It's both possible that the first byte here equals 1, meaning we continue executing the function, or that it doesn't equal 1, and that we immediately return. And the way symbolic execution handles that is it takes this if condition and it forks the execution of our program. And in the first fork of the program, we assume that in this case, the first byte doesn't equal 1. And in that case, we reach the return instruction and immediately exit the function. In the second fork of the execution, we assume that the opposite condition is true. We assume that the first byte does equal 1. In this case, we continue exploring the execution of the program, and now we enter the other branch of the if test, meaning we continue executing our program. So another way to illustrate this is we start using only one state of the execution, and when we hit a branch that is based on symbolic input, we fork the state. And in the first state, we assume the condition is true, and in the other state, we assume the condition is false. Now, While analyzing a program in this way, we need to track all the conditions that we assumed the symbolic input adheres to. So, for example, in our first fork, we assume that the first byte doesn't equal 1. In the second fork, we assume that the first byte does equal 1. And all these conditions that we assumed, we call those the path constraint. And to put that in different words, if we are exploring a certain path of the program, the path constraint basically specifies all the conditions that must hold for the program to take a certain path through its code. And in our case, in the first fork of the execution, we immediately hit the return statement. And in the other fork of the program, we continue executing the function, and we now hit the second branch, which again is based on a symbolic input. And here we do exactly the same. We have a branch on symbolic input, meaning we fork the execution. On the first fork, we assume that the second byte doesn't equal the length of the packet. And on the third fork, in this case, we assume that the second byte does equal the length. And here in the middle case, we immediately hit the return function because the header is not valid, and we immediately drop the packet. In the third case here, in the third state, we continue exploring the function. And that means we hit the following line of code where we are dividing the length by a certain byte in the payload of the packet. And the question we can ask here is it possible that our implementation will ever crash on this line? In other words, can it be that this third byte here equals 0? Well, we can ask our symbolic execution if that's the case. We can ask our symbolic execution engine, hey, is it possible that the third byte here, which is stored at offset 2 in data, that it equals 0? Is that possible under the current path constraint, meaning under the current assumptions we made? And in this case, our symbolic execution will internally use an SMT solver to check this question, and it will say, yes, it's possible that this byte can be 0, meaning you possibly have a division by 0, and your program has a bug. Now, instead of implementing our own symbolic execution engine on our own SMT solver to answer these type of questions, we relied on an existing symbolic execution engine, and the name of that engine is called CLI. And the reason we use this is because it's actively maintained, and the other advantage is that it works on LLVM bytecode, meaning we can take a protocol written in C, compile it to LLVM, and then analyze it. But we can also take an implementation in, say, Java, compile it to LLVM, and it would again be possible to analyze it using CLI. Now, symbolic execution has a lot of advantages. It can explore all the paths of a program. However, it's no silver bullet. It also has quite some disadvantages. And the big one here is that if you have a large program, the program can be in an exponential amount of states. The more if conditions you have, the more branches you have, the more states you need to explore, and this quickly becomes infeasible. So in practice, that means we can symbolically execute small to maybe medium-sized programs, but a large program like a complete web server or Word or something like that, you cannot use this using the approach we discussed. You need a lot of optimizations to simplify this. Another problem is that your program may enter infinite loops. For example, if you're processing a linked list and trying to search for an item, it's possible that you keep that the linked list is of infinite length and your program becomes stuck in an infinite loop. But another important problem is the so-called SMT query complexity. Now, what do I mean with this? Well, in the example I just illustrated, we asked this question to our symbolic execution engine whether a certain value could be equal to 0. And an SMT solver is used to answer these type of questions. Now, in our example, this was a very easy condition to check, but you can sometimes have very complicated properties that you want to check, and that can take a very long time. But if we analyze a fairly small program, for example, the main functions of a network protocol implementation, that is feasible to do using current tools. There is one problem that arises if we apply symbolic execution to, for example, a network protocol that uses cryptography. And I will illustrate that using this example. So it's again a function that receives input from the network. And let's say we take exactly the same approach as before. We mark here the data packet as being symbolic and then perform symbolic execution of the function. Now, at a high level, what happens when we symbolically execute the decrypt function is that our symbolic execution engine will try to summarize what this encryption algorithm is doing. And depending on the specific encryption algorithm we are using, this can take a lot of time to construct this summary of the function. Meaning, if we use a certain encryption algorithm, we will never finish analyzing the decryption function. Now, let's for now assume that we are using a decryption function which we can summarize efficiently, meaning we now will try to execute the remaining parts of this function. And then the second situation where it can go wrong is that we now want to check whether a certain decrypted output can be equal to some value. For example, here, whether the first byte is equal to the magic value of the command. And again, this can take a lot of time because now our SMT solver, so our symbolic execution engine, needs to analyze the encryption algorithm and it needs to decide, is it possible that this decryption algorithm results in this specific plain text output? And this can again be very time consuming, meaning we won't reach the interesting code that we want to test. We won't reach the code that will try to process the decrypted data and maybe try to parse binary data that is stored in there. So the question is, how can we overcome this problem? Well, it turns out that it's actually very easy to overcome this problem. We simply treat the decrypted output as a fresh symbolic variable. Now, another way to look at this is that you simply do not execute the decrypt function at all. You just replace it by a stop function that is nothing. So to come back to our example, when we use this technique, we would again mark the incoming data packet as being symbolic. But now instead of trying to summarize this decryption function, we simply treat it as returning a fresh symbolic output, meaning the remaining analysis of this function is quite easy to do. Meaning we can now analyze, for example, the process command function. Now, apart from handling decryption functions in this way, we can also handle hash functions in the same way. We don't actually execute the hash function. We simply pretend that it returns a fresh symbolic variable. And this also works to handle HMAC functions, which return on an authenticity tag to verify that the packet is really from the sender. Another thing we will do is we will track whether certain crypto primitives are used in a correct way. For example, let's say you have an older network protocol which, say, uses RC4 for encryption and then uses HMAC SHA-1 to verify the authenticity of a packet. The problem here is that a developer may forget in certain very peculiar parts of the program is that the developer may forget to check the authenticity of the HMAC output, but it might still decrypt the content of the packet and then process it. And in order to detect these kinds of things, what we will do is we will track which crypto primitives are used in a program, and specifically, we will record the relationships between inputs and outputs. So we will record the input of a hash function and we will mark the relationship with the output of the hash functions. So we know that the output of a hash function is the result of hashing a certain input, basically. And this allows us to detect interesting vulnerabilities. And I will come with more concrete examples in a bit, so don't worry if this is a bit unclear to you now. One thing we can do using this is we can discover timing side channels. For example, a very common mistake that is sometimes made is that a non-constant comparison is used to verify the output of a hash function to verify an authenticity tag. And we can detect this by checking if there are certain paths in a program where only a few bytes of an authenticity tag are included in the path constraint. Because if that's the case, it means the program compared a few bytes of the authenticity tag and then stopped comparing the rest, meaning it's not a constant time comparison that it's using. The second type of vulnerability we can discover is specific types of decryption oracles. And a decryption oracle here, what I mean with that is that sometimes a program will perform operations based on decrypted but unauthenticated data. So a common example here is a program will not check the output of the HMAC function, it will not check the authenticity tag, but it will, for example, decrypt the payload using RC4 and then process it. That is something that may happen in older legacy code. Okay, so that concludes the quick overview of symbolic execution. And our idea is now to apply this to the four-way handshake of Wi-Fi. So now you may wonder, okay, what is this four-way handshake? What does it do? Well, the four-way handshake is used by all protected Wi-Fi networks, and it provides two things. It provides mutual authentication, meaning the client has to prove that it possesses the correct credentials, and the client also verifies that you are connecting to a legitimate access point. And at the same time, the four-way handshake negotiates what is called a PTK, and that is just a session key. It is the session key that will be used to encrypt data frames after the four-way handshake has been executed. And this session key will also be used to protect certain messages of the handshake itself. And an important remark here is that this four-way handshake is used for any protected Wi-Fi network, like I mentioned. So it's used both at your home network, but also at an enterprise network where you, for example, have to log in using certificates, or where you have to log in using a username and a password. So how does the four-way handshake work? Well, let's assume we have a smartphone here and it wants to connect to a router to a Wi-Fi network. In order to execute the four-way function, we first need to have some shared secret between the client and the access point. And with a home network, that shared secret is simply the password of the Wi-Fi network, so that's the easy case. If you have an enterprise network where, again, you have a login, for example, using a username and a password, there is first an 802.1x authentication stage, which negotiates a secret between the client and the router, or between the client and the access point. Now, how this works in detail, we don't need to know. We simply can assume that there is some shared secret between the client and the access point. And once we have that, we can start performing the four-way handshake. And as the name of the four-way handshake implies, it consists of 4 messages. And the first 2 are used to transport a random number between both devices. So we can see here, first the access point sends message 1 to the client, and it contains the A nonce, which stands for access point nonce, and it's just a random number. The client, when it receives that message, will also generate a random number called the S nonce, which stands for supplicant nonce, where supplicant is just a synonym for client, and it will send that to the access point. And once both devices have these random numbers, they can derive the PTK, the session key, by combining these random numbers with the shared secret. And then the last 2 messages of the handshake, simplified, they are simply there to confirm that both parties negotiated the same session key. And message 3 does one thing more though. It also transports the GTK, which is the group key. And the group key is used to transport broadcast and multicast frames in the network. And the access point gives the current group key of the network to the client in message 3 of the four-way handshake. And once this all completed successfully, both parties can install the session key, meaning they can now send encrypted data frames. Now, remark here that the client already derived the PTK, the session key, after receiving message 1. And the access point can also derive the PTK after receiving message 2. And This actually allows us to already protect handshake messages under the current session key once we received message 1. So to put that in a different way, the last 3 messages of the handshake are authenticated using a MAC, using an authenticity tag, which is calculated under the current session key. Okay, so that's a very quick introduction of the 4-way handshake of Wi-Fi. We now want to analyze implementations of it to detect vulnerabilities in this handshake. More specifically, we're going to focus on 3 Wi-Fi clients. The first one is the Intel IWD client. It's a fairly new client which has existed for, I think, roughly 3 years. So it's not widely used yet, but I expect that in the future more people will use it. And I have to say the code of this one is quite clean, so I expected to find few vulnerabilities in this one. And that was indeed the case. We didn't find many issues in this implementation yet. The second implementation we will look at is WPA supplicant. And this one is the most used Wi-Fi client in open source distributions. It's used in nearly every Linux distribution. It's used on your Android phones as well. And it's also used by routers if they, for example, support client functionality. And the third client we will investigate is the MediaTek kernel driver, which is used in certain routers and Wi-Fi repeaters. And the interesting part of this is that it's actually leaked code. And the other thing that makes analyzing this implementation challenging is that it's a kernel driver. And this complicates our symbolic execution, but we'll come back to that in a minute. The question is now, how can we get these working under CLI? Let's say you want to use symbolic execution yourself. How much work would you have to do in order to carry out this type of analysis? Well, with Intel IWD, there are 2 approaches possible. One approach is to run the full program symbolically, but that would be quite hard to do in practice, because then we would have to simulate the complete Wi-Fi stack of Linux, so we could also symbolically execute that. And that's a ton of work. You don't want to do that, and I didn't have the time to do that. Unfortunately, there's a second approach that's possible. Namely, what I did is, well, I noticed that IWD had very nice unit tests, and these unit tests initialize a very small state of the program, basically enough state to execute the 4-way handshake. And this is very good for us, because we can simply take that unit test, and instead of then running these unit tests with concrete 4-way handshake packets, we can simply provide symbolic 4-way handshake packets, and that's it. We can then symbolically analyze this implementation. So analyzing IWD is quite straightforward, in my opinion. We also have WPA supplicant. Now, this one also has unit tests. So my first idea was to do exactly the same as IWD, simply take the unit test, symbolically execute it, and see if we find vulnerabilities. Unfortunately, this unit test uses virtual Wi-Fi hardware, meaning we would again have to symbolically execute the Wi-Fi stack. And we don't want to do that because doing that requires a lot of work. So we were inspired by the IWD case, and we simply wrote our own unit tests, which initialized relevant parts of WPA supplicant, and then executed the 4-way handshake. So then we could provide a symbolic packet and analyze the code. Now the third one we want to symbolically execute is the MediaTek driver. And without going into too much detail here, it's again a kernel driver, meaning if we would do it the dumb way to put it, then we would have to fully symbolically execute the complete Linux kernel, which would again be a ton of work. So inspired by our previous cases, we simply took the kernel code, we simulated it in user space, and we were able to perform symbolic execution like that. So that went quite well. It took some work, but that works. Now, there's one remark I want to give here. The first one is parts of our codes are available online at the following URL. And an important remark here is that if you look at my code of IWD, it's quite clean and understandable. But if you look at my code where I simulated the MediaTek driver in user space, you're probably going to wonder at some points what on earth I was thinking when writing that code. But, well, our approach does work, so we can symbolically execute it, so let's focus on that. Okay, so that was quite a lot of background. Now we get to the really interesting part of the talk, so if you happen to have fallen asleep, now is the time to wake up. So our first result is that we detected that some implementations were indeed vulnerable to these timing side channel attacks, where we had a comparison which exits on the first byte difference, and this allows us to time how long an implementation needs to verify the authenticity tag, and based on that timing we can byte by byte guess the authenticity tag. And we found that MediaTek and IWD were vulnerable to this. Now, even though in theory this vulnerability is in the code and it should be fixed, in practice this will be hard to exploit. The first reason is that these timing differences are very small, and over a Wi-Fi connection it would take a ton of connection attempts to measure this very small difference. On top of that, most libraries and implementations don't compare two buffers byte by byte. They actually compare 4 bytes at a time for efficiency reasons, meaning an attacker would have to guess 4 bytes at once, which is infeasible to do in practice. So I believe that this is not exploitable in practice, but it is something that should be fixed. We also found a small denial of service attack against the IWD Wi-Fi client. Basically, there's an integer overflow. This causes a very huge memory allocation, and because this allocation fails, IWD will abort its execution and close down. Now, probably one of the most interesting vulnerabilities we've found is a buffer overflow in the MediaTek driver. And this overflow occurs when the client receives message 3 of the 4-way handshake, and then a stack-based buffer overflow occurs, and this will lead to remote code execution on the victim. And we will discuss in a few slides in detail about how we were able to exploit this vulnerability in practice. Another vulnerability we found is one that we found manually while inspecting the code. And here we noticed that MediaTek was wrongly implementing a certain cryptographic primitive, which is here called the AES unwrap primitive. And this would allow an attacker to forge certain frames of, I think it was a proprietary network protocol. I'm not sure about the details. But it's another bug in the code of MediaTek. Then the last bug we found, and it's also a very interesting one, and we will discuss this one in detail later on in the talk as well, is that we found a decryption oracle in WPA supplicant. And remember, WPA supplicant is used in nearly all Linux distributions and Android as well. And the problem here is that the authenticity of message 3 is not being checked. However, the payload inside message 3 is being decrypted and processed. And I will discuss in a bit how this will allow us to decrypt the group key that is transported in message 3. But first, I'm going to explain how we were able to use the stack-based buffer overflow of the MediaTek driver to remotely compromise a device. Now, before I'm going to discuss that, we first need to know what are the preconditions. When can I exploit this vulnerability? An important remark here is that this happens in the client functionality of the driver, meaning we either have to exploit a Wi-Fi client, or we can exploit a Wi-Fi router that has repeater functionality to extend the range of another Wi-Fi network. Another condition here is that the adversary needs the password of the network. Now, you may be wondering now, when is it useful as an adversary to have the password of the network and that there then is someone you want to attack? I mean, take for example your home network. You only give out your password to people you trust. So when is something like this useful in practice? Well, if we look at how Wi-Fi is used, we see that a lot of conferences on hotels, they simply set up a protected Wi-Fi network and they share the password to everyone. This means that you share the same password as someone else you do not trust at all. So this even happens a lot at security conferences where you have a protected Wi-Fi network, but the adversary will know your password as well, meaning the adversary can try to attack you using this attack. Now, there is another condition here, and that's of course the victim you want to attack needs to run this vulnerable code. Otherwise, yeah, of course, you're not going to be able to attack them. And I would say here we got lucky because this MediaTek driver is not included in the Linux kernel source tree by default. It's only used in more proprietary routers where the manufacturer itself added this driver to the Linux kernel. So we got lucky there because otherwise maybe all Android phones or Linux distributions would be vulnerable. But instead it's only specific routers that we can attack. So in particular we can attack routers that have a repeater functionality or simply dedicated Wi-Fi repeaters. We can attack those as well. And I'm now going to discuss how we applied the exploit against this specific router, the RTAC51U. And I'm going to assume it runs the Padavin firmware. Now, you may not have heard about this firmware before, but the firmware is similar to DDWRT and OpenWRT, except this firmware is less known because it only is able to run on a very specific set of devices. And the reason why we assume that this firmware is being used is because the original function of this device is very limited and it doesn't have this repeater functionality. I do want to remark here that other routers of MediaTek do have this repeater functionality by default, but unfortunately I didn't have those routers to test, so I had to rely on this setup. But anyway, if we look at how many devices use this Padavin firmware, we actually can see that quite a lot of them are running it. This one doesn't show all the possible versions that we have, but in total it has more than 100,000 downloads. And the specific version we are going to attack has more than 50,000 downloads. At least downloads that happens directly through Bitbucket. And we want to exploit this specific version of the firmware. And to do that, we first need to know a bit more details about the vulnerabilities. I mean, we know it's a stack-based buffer overflow, but we need some more detail. So let's look at the function where this vulnerability occurs. Now, this is highly simplified code, and to help you a bit, the vulnerability occurs in these 3 lines. So we can see here on the first highlighted line, we declare a buffer on the stack of a fixed length. We then here calculate the length of the group key that is transported in message 3. And this length can be controlled by the attacker. We assume here that the attacker is a malicious access point, which is able to send any type of message 3 that it wants, and the attacker can include a very large group key inside that message. And the receiver here, the client, does not verify the length of this group key. It simply performs the function endThisMoveMemory, which is basically just a fancy name for a mem copy. And yeah, the destination buffer is only 32 bytes, but we can have a group key of up to 250 bytes, meaning we get a stack-based overflow. And we were able to exploit this to remotely compromise a device. And it turns out that the exploit here contains quite a few stages, and we'll discuss them in high level how they work. Namely, we first have to get code execution in the kernel, in the driver. Then we need to obtain a process context so we can inject ordinary shell code to then spawn an ordinary remote shell. But let's just get started with the first step. We want to abuse our stack-based buffer overflow to get code execution in the kernel. So the question here now is, okay, how hard is it to control the return address of the function, and if we can control it, where do we return to? Well, controlling the return address is actually trivial because there are no stack canaries, there's no kind of protection, so we can just provide a long group key that overwrites the stack, and there we go. We now control the return address, so we can control the instruction, we control the program counter of the CPU. The second question is, where will we put our shellcode, and then at which address can we put our shellcode, and where can we execute data? And here again, things seem very easy because the kernel of our firmware, at least the kernel stack, has no address randomization, meaning it's always loaded at exactly the same location, and the stack is executable. So if you look at this, you're probably thinking, this is a walk in the park. Just put the shellcode on the stack, return to it, and we're done, right? It turns out, if we do this, our shellcode crashes. And that's very surprising because it's very hard to debug this because we're working on an embedded device. But if I would have attached a debugger to it, I would have seen that I indeed control the program counter, meaning I'm returning at the correct address. And when I then inspect the memory at this address, my shellcode is indeed there. And this shellcode then would work under my debugger. But it doesn't work when actually performing this attack. So what on earth is going wrong here? Well, after thinking about it a bit and looking at some related work, it turns out that this is because of cache issues on the specific CPU we are attacking. Namely, we are attacking a CPU which has a MIPS processor, and the interesting thing about this processor is that it has a separate data and instruction cache. So what is happening here? What is going wrong? Well, we have our data cache, and when we trigger our stack overflow, our shellcode is indeed written to the stack. However, it is only saved in the data cache. It is not yet flushed to the main memory. Which means that if we now point our program counter to this stack address, our CPU will look up, okay, is the instruction at the stack address in my instruction cache? No, it is not, because the program never executed code from the stack before, meaning it will then fetch the instruction from the main memory. But the main memory still contains the old stack data, meaning we're just executing random data, and that's why our exploit doesn't work. And fortunately, there's an easy way to fix that. After writing the shellcode to the stack, we simply have to flush the memory. We have to flush this to the main memory, so our main memory contains the shellcode. And when we then return to the stack, we will fetch the correct shellcode from the main memory. So now the question is, how do we flush the stack? Because, we cannot execute code on the stack. So what do we do? Well, here again, we have a very popular technique. We will use return-oriented programming to call a kernel function that will flush the stack for us. And here for the MIPS architecture, we can use a tool of Craig Hefner to find all the ROP gadgets that are present in the code. But without going into too much detail, it's possible to achieve this. It's possible to flush the cache using ROP gadgets. I found it quite tedious to construct this, but we were able to do this. Which means we can now execute shellcode in the kernel. But now we get to our second stage. Even though we now have code execution in the kernel, we want to spawn a traditional remote shell so we can run all our traditional attack tools. And it turns out that spawning a new process in the current state we are in is quite hard. Because right now, our CPU, our kernel, is performing operations in function of the Wi-Fi chip, in a sense. In other words, it's executing in what we call an interrupt context. And in an interrupt context, it's difficult to spawn a new process or to take over an existing process. It's much easier when the kernel is operating in what we call a processor context. And in a process context, the kernel is performing operations, in a sense, in name of a process. For example, if there's an application that performs an open or a closed system call, the kernel will perform these functions in name of the process. And in this context, it is much easier to then spawn a shell, a normal user space shell. So the question is, how do we obtain a process context? Well, again, this is actually quite easy when you think about it. We can simply intercept certain system calls. And in particular, we intercepted the closed system call. And if we then, so we intercept this system call, and we can then include code in our interceptor in a sense. And when this interceptor is running, we know we are operating in process context. So let me illustrate that in a different way. The kernel implements system calls using a system call table where it can look up the identifier of a system call, and in that table there's a pointer stored to the function that performs the original operation of the system call. And we can intercept these system calls by simply pointing this pointer to our own shellcode that is located somewhere on the stack, and is located on a place on the stack where it doesn't get overwritten quickly. And the idea is very simple. In our interceptor, we can perform the extra stages of our attack, and after that, we simply jump to the original system call, so all other applications work normally. So, okay, to recap, we exploited our buffer overflow. We have control over a program counter. We can use this technique to then obtain a process context. And the advantage of obtaining a process context is that we can now inject shellcode into that process. Now, one important remark here is that we don't just want to hijack any process that is running on the router, because then maybe the router will crash or it will restart or something goes wrong. So what we do is we look for an unimportant process, and in our case we have a process called detect linked, which simply does a very mundane task, and if that process gets replaced by our shell, the router will just continue functioning as normal. And we can recognize this process because it always has a predictable process identifier. It has a predictable PID. So once we are operating in this process context, it's very easy to inject our shellcode, because from inside the kernel, we can now access the address space of our process, meaning we can just call mprotect to make the code of the application writable. We can copy our shellcode there. And there's again one thing we need to remember. After copying our code, we need to flush the caches. But if we do that, we can now run our injected shellcode into the user space process. And in my case, I just executed telnetd as a remote backdoor, meaning an attacker can now connect to a port 1337, and it will then have full control over the router. So as I mentioned, one important remark here is that the original process will be killed, but this causes no problems. And the reason why I use telnetd instead of a reverse TCP shell is because simply spawning telnetd resulted in some smaller shellcode, which makes the attack more, well, basically easier to pull off. So this is a multi-chain exploit. You had to see that we had to perform several steps. So you may be wondering now, is there enough space to put all this shellcode onto the victim machine? And here we have that for our initial stage, where we trigger our stack-based buffer overflow. We have 250 bytes that we can use. So that's enough for the first stage. And on top of that, we can also carry a lot of payload in message 3 of the handshake message itself, because in total it can transport more than 2,000 bytes. On top of that, what makes the attack also a bit easier for the adversary is that we can include null bytes in the payload, because the vulnerability is triggered by a mem copy. So this also makes our shellcode a bit smaller in practice, which means, to conclude, yes, we can indeed exploit this, and all our code fits, and we can deliver all our shellcode to our victim. And you can see here, it's just a screenshot. Unfortunately, I didn't have time to prepare a demo here, but this attack worked against a specific firmware that we were exploiting. Now, I have to mention one limitation, though, of our attack is that we currently assume hard-coded addresses that are used in this firmware version. So if you want to attack another version, you will have to update the exploit. Now, I want to conclude this part of the talk, the exploit, with a few important observations, which I think are useful for people that are maybe exploiting devices like this for the first time. The first one is that you should remember, you should check if the architecture you are attacking is affected by this cache incoherency problem. The other thing I would recommend people new to performing these types of attacks is first test your code in C. Especially if you have a multi-stage exploit like the one I had, it's easy to just test IDs in C, see if they work, and only then convert them to assembly. Another clever trick I found is that sometimes you want to debug your shellcode, but in my case, it was very annoying to attach a debugger to my router, and in certain cases, I also couldn't provide debug prints. So it was very hard to debug my shellcode because I couldn't use any of the traditional debugging techniques. Now, one trick I used is I simply included some infinite loops in the code. And this allows me to see how far my shellcode works. Because if I put my shellcode in the middle of, if I put my infinite loop in the middle of the shellcode, and then I notice that my router indeed gets in an infinite loop, I know that my exploit works until that stage. However, if my infinite loop would not be hit, then I would know, okay, I don't reach that code, my bug is above the infinite loop. And this is a very clever, small little trick that's really useful in practice. The other thing I want to mention here is if you want to do these kind of exploits on your own, I really recommend doing the challenge on io.netgarage.org. They have a lot of challenges ranging from very basic ones to really advanced ones, and they are very useful to learn these types of attacks. Okay, so that covers the remote exploitation of our driver. I'll now discuss how we were able to attack WPA supplicant by performing a decryption oracle attack. So let's first recap. The vulnerability I found in WPA supplicant was that this Wi-Fi client doesn't verify the authenticity of message 3, but it does decrypt the payload and then tries to process it. So now the question is, how can we abuse that kind of behavior to leak data? And in order to answer that question, I first need to explain how a normal receiver processes a message 3. So let's say we have the following message 3 here. It's a very simplified layout. We simply have a header, and then we have the payload of message 3, which is authenticated unencrypted. The first thing that the receiver will do is it will, of course, decrypt this key data field where the payload is saved, and then it will process the payload that is there. And here, the payload is essentially a list of type length value elements. Now, what do I mean with that? Well, these type length value elements, they are parsed in the following way. The receiver first reads the first 2 bytes of the payload, and these first 2 bytes represent the type and the length of the next element in this payload. So my example here, the length of the next element is 18. So the receiver will then check, okay, are there still 18 bytes left in our payload? In this case, yes, there is. So up to this point, we have successfully parsed the first element. We can see that there's still payload left, so we continue parsing the next element, meaning we first read the type and length field. In this case, we have an element of 38 bytes, and in our example, the receiver will again check, are there indeed 38 bytes left? Yes, there are, and we now end up exactly at the end of our payload, meaning our processing completed successfully. So at this point, the receiver can extract the group key from this payload, uninstall it. So now the question is, how can we turn this parsing behavior into an oracle where we can then leak data? Well, to explain this, I'm going to simplify the layout of message 3 a bit, and I'm just going to assume that there's only one element inside message 3, and it's the group key of the network. And a very important remark here is that this means an adversary knows the first 2 bytes that are encrypted. The adversary knows that the type and length equal these 2 specific values. Even though message 3 is actually encrypted, the adversary knows these plaintext bytes. And this is very important because the encryption algorithm that is used here is RC4, and it's a stream cipher. And to put it in a simple way, if the adversary knows the original plaintext byte that is encrypted, it can manipulate the encrypted version of the packet to change the plaintext value that is stored in the packet here. In other words, if the adversary knows that, in this case, the length is 38 bytes, it can then manipulate the ciphertext and turn this, for example, into 36. And the receiver will not notice that we manipulated the ciphertext because of the bug, because the receiver doesn't verify the authenticity of the frame. So we can indeed modify the ciphertext in this way. And what we did here is we decreased the length by 2. And this means something very interesting will now happen when we parse the payload. Because when we now parse the first type length value element, we will again read the first 2 bytes. We will see, okay, this element is 36 bytes long. Do we have enough space for that? Yes, we do. So the first element is parsed successfully. However, there are now still 2 bytes at the end that are remaining. And again, the receiver will try to parse these. So it will again determine the type and the length of the next element. But now we notice we're already at the end of the payload, which means that parsing will now only be successful if the length here is 0. Because if the length of the next element is larger than 0, the receiver will say, hey, that's not possible because I'm already at the end of my packet. This means that if this last byte here of the packet, and we don't know the value of that byte, but if that last byte is equal to 0, parsing will succeed. And if it's not equal to 0, parsing will fail. And that's the technique we will use to recover the group key byte by byte. So to put it in another way, what the attacker will do is it will guess the last byte of the packet. And remember the property of our encryption algorithm. If we know a certain byte that is being encrypted, we can change its plaintext value, even if we don't know the encryption key. So what the attacker can do is it can guess the plaintext byte that is present at the end, can then try to change it to 0 based on its guessed value. And if it guessed correctly, parsing will succeed, and the victim will reply using message 4 of the handshake. If the attacker guessed wrongly, the receiver will drop the packet because parsing fails and it will not get a reply. And we can keep doing that byte by byte until we guessed all bytes of the group key. So if you do that in practice, it takes about 14 seconds to verify one guess. So that's actually a lot of time, because that means it takes about 8 hours to recover a 16-byte group key. However, there are techniques to make this attack faster. For example, we can attack multiple clients at the same time, and instead of recovering all the bytes using our decryption oracle, we can simply recover the first 12 bytes and just recover the remaining 4 bytes using a brute force attack. So that covers all the vulnerabilities that we found. So as the last slide, I want to zoom out a bit and look at the big picture of the research we are doing. And I think this is very nicely illustrated by the comic here. It's I think this one is about 4 years old. I don't know exactly, but basically it says that there's this guy that wrote his own symbolic execution engine, which does a lot of fancy stuff to then find one vulnerability. And he then looks at this other researcher and he says, oh, this other guy just wrote a very dumb fuzzer and he found more vulnerabilities than me. So this is basically an illustration that it used to be that, yeah, symbolic execution is nice, but you had to put in a lot of effort, and generally traditional fuzzing sometimes had better results. What we notice now is that our symbolic execution tools are becoming better, meaning we don't need to put in as much effort to get symbolic execution working, meaning our tools are becoming more performant, they are more usable, more efficient. So slowly, symbolic execution is becoming a good alternative. Now, we're not there yet, but step by step, we are getting there. Now, there's also some future work, but this is a bit more academic, so I'm going to skip that. And with that, I can conclude the talk. So what I talked about is symbolic execution of network protocols. We were able to handle network protocols that use cryptographic primitives. And we have two very nice attacks. We have a root exploit, because we gain admin privileges on a device that runs our vulnerable MediaTek driver. We have an interesting decryption oracle, and these two exploits, by the way, they're already patched. However, we know that some Android phones, and especially routers, they are not updated frequently. So in practice, it might still be possible to perform these attacks, even though they may not be very practical. In all cases, I expect that some devices can be compromised using these attacks. And finally, I think this is an area where we can do a lot of interesting future work. So with that, thank you for your attention.
Thank you very much, Mathy.